Hi, my name is Marcel Désor, and today I want to present a screencast of the presentation that I gave at the Symposium on Thermoacoustics in Combustion in Trondheim this year. The topic of this talk is the large eddy simulation of thermoacoustics for premixed partially cracked ammonia flames, and we've worked on this together with my colleagues Nada Shodi and Diana Lacoste from KAUST in the group of Wolfgang Polivke at TU Munich. All simulations shown here were performed on the supercomputers at LRZ in Garching. To dive right in, I will give you an outline of what you can expect from the next 15 to 20 minutes. Firstly, I will present results that we've obtained from fitting a global mechanism for use in premixed ammonia flames. Then we applied this global mechanism in a large eddy simulation-based setting in order to extract the flame transfer function of ammonia flames using system identification. And afterwards, I performed some benchmarking of the thickened flame model in order to find out what are the modeling parameters that impact flame predictions the most. Okay, why do we care about ammonia in the context of thermoacoustics? Well, if we want to burn ammonia in a gas turbine combustor, for example, if we want to mitigate peak loads in the morning or in the evening, we could burn it directly. However, ammonia burns really poorly and is hence prone to blow off, or in general limits the operability range of the gas turbine, and additionally it has very undesirable flame characteristics, yielding very long flames that are prone to, for example, flame wall interactions. However, one way we could burn ammonia anyway is if we crack this ammonia upstream of the flame. This way we crack the nitrogen-hydrogen bond upstream of the flame, releasing the molecular hydrogen as a way more reactive fuel part. This way we can effectively reduce the flame length, making it compact again already at relatively small amounts of cracking. However, this comes with a downside, and that is we go from the desirable characteristic of not featuring thermoacoustics at all with pure ammonia, at least in this combustor, to having very significant flame transfer function gain again, already at 28% of cracking. Now, if we want to predict the thermoacoustic instability using a CFD-based approach, first of all, we need an adequate representation of chemistry. And for your typical CFD simulation, the direct use of detailed chemical schemes such as the one by Stagni et al. From 2023 is unfeasible because they are very expensive to compute. For this work, we opted to optimize a global chemical scheme, 2 reactions, 5 species, in order to represent chemistry as cheaply as possible. We optimize this chemical scheme using an established approach where we optimize the rate coefficients in the Arrhenius equation in order to optimally predict reaction rates. And you can see we nicely predict laminar flame speed, laminar flame thickness, and adiabatic flame temperatures in the lean regime here. Once we go to the rich regime, we overpredict the flame speed, and once we extrapolate the cracking ratios, you also see a very significant deviation. However, we can make use of the pre-exponential adjustment technique that was introduced by Francelli et al. In 2012, and this way we can reproduce key flame characteristics relevant for thermoacoustics across variable equivalence ratios and variable cracking ratios. The setup that we investigate everything on is a fully premixed swirl stabilized flame. On the top left you see the numerical domain as an overview, while on the bottom left the corresponding experimental setup is shown, and on the right you see the meshing approach that we used. In the flame zone and the swirler region, we use a characteristic grid size of 0.4 millimeters, while on the walls we employ finer grid cells of 0.2 millimeters to resolve boundary layers. Further up and downstream, we don't resolve the mesh as fine with a characteristic size of 0.8 millimeters. Here you see line of sight integrated time averaged heat release rate from the large eddy simulation and line of sight integrated OH star chemiluminescence image from the experiment. While heat release rate and OH star signal intensity are not perfectly proportional to each other, OH star still gives an indication of where is the reaction zone. You can see overall that for small amounts of cracking, so for alpha equals 0 and alpha equals 0.1, the flames are overall too short. This is worse the less cracking we have. So for the pure ammonia flame, the flame is significantly too short, while for alpha equals 0.1, the flame is still too short, but it's not as bad as for pure ammonia. Once we go to alpha equals 0.28, so 28% of the ammonia by volume is cracked into hydrogen and nitrogen, you see we get a very nice representation of both flame length and flame width. Then we wondered, why does the global mechanism in conjunction with LES predict a pretty good flame shape for alpha equals 0.28, while it fails to do so for alpha equals 0.1 or alpha equals 0? For that, we looked at the counterflow premixed flame in the fresh to burnt configuration, and we analyzed the consumption speed normalized by laminar flame speed versus strain rate. And you see here that for pure ammonia, we have a positive Markstein length in the detailed scheme, while the global scheme, it does predict a positive Markstein length, but we predict significantly too high consumption speeds. For alpha equals 0.1, there exists a small region of negative Markstein length at very small strain rates, while for higher strain rates the Markstein length reverses and the flame slows down with increasing strain. This is also inadequately captured by the global chemical scheme at 10% cracking, hence we still predict flames that are too fast. At a cracking ratio of 0.28, there seems to be a balancing effect, so we do predict negative, or the detailed chemical scheme does predict negative Markstein length at moderate strain rates up to about 1000 per second, while it does predict the negative Markstein length for anything beyond, while our global chemical scheme seems largely unaffected by strain altogether. So we predict too slow flames for small strain rates, while we predict too fast flamelets for high strain rates. Overall, this seems to compensate at alpha equals 28%, which is why we predict a good flame shape. Then let's look at the flame dynamics. On this slide, I present the flame transfer function as computed by LESSI versus Struhal number, and we chose Struhal number in order to compare if we represent the correct physics, even though the flame length is different. And you see for pure ammonia, the alpha equals 0 case, we do predict that we have one overshoot in gain with a linearly decaying phase. Do note here that the uncertainties encountered are very, very large, and this owes to the fact that the flame is so long that a Struhal number of 0.5 corresponds to approximately 50 Hz. So even if we excite for a very, very long time series length with the broadband signal, there is very little coherent dynamics that the flame exhibits. For alpha equals 0.1, we do predict nicely the first overshoot in gain. We don't predict the second bump, and why that is still under investigation. We're not quite sure yet. However, until a Struhal number of about 0.4, we predict the physics quite nicely. Now for alpha equals 0.28, we do predict the entire FTF gain across all frequencies reasonably well, while we do predict the phase until the Struhal number of about 1 and a phase shift of pi over 2 afterwards. Do note here that because the flame is very similar in length to the experiment for alpha equals 0.28, this is also true for frequency, not only for Struhal number. Now let's come to the last part of this talk, which is the benchmarking of the thickened flame model. The basic idea of the thickened flame model is if we increase diffusion of species and the thermal diffusion by the factor F, while at the same time reducing every source term by the same factor F, we can conserve the laminar flame speed while we increase the flame thickness. In practice, this F is typically computed by the dynamic formulation here, where the user inputs the factor N, which is sort of the target resolution that the flame should achieve on the given grid, and together with the LES grid size and the laminar flame thickness, F is then computed. On the bottom left, the connection between these parameters is illustrated, where the dark red curve is a wrinkled flame that would be too thin for the grid given here, And if we now set n to about 3.5, so you see here the light orange flame is a bit thicker than 3 times the grid size, we then achieve a thickening factor F of about 7. So while connected, F and N are not the same. And the reason why I talk about this is if you look at this laminar flame here, this is just a laminar slit flame stabilized at an adiabatic slit here. As soon as we thicken this flame, so on the left you see an unthickened flame, on the right that same flame is thickened by F equals 2, you see the flame transfer function starts decaying significantly earlier than it should if we apply the thickened flame model. This is true for the gain, but luckily not the phase. And the question then that sparks is, how relevant is this actually in applied turbulent flames? The reason I talked about all of this is ammonia flames have one very nice feature regarding numerics, and that is they are very, very thick. At the present configuration, the laminar flame thickness of the 28% cracking flame is about 0.7 millimeters, which means we don't need any turbulence chemistry interaction model. We can get away with a fully flame resolved simulation. So I created 3 meshes from the baseline mesh that I've shown you before. I refine once the flame region and the swirler region, and then I refine the flame region once more, cutting the cell size in half every time. This way, we can systematically vary the thickening factor in 2 ways. One is we fix N. Remember, N is the resolution that we want to have in the flame zone, or the number of grid cells that we want our flame to be resolved on, basically. And we can fix N and change the mesh, here by changing the thickening factor from 1 to 2 to 4. We can also fix the mesh and change N on the mesh, here by changing on the medium mesh, for example, F from 2 to 2.8 to 4.2. We do this partially because there is another open question in the thickened flame model, and that is, how do we pick this factor N? In the literature, you will find values for N anywhere between 5 to 12, so there is not really a gold standard value that is usually employed. Okay, let's jump into results. Here you see the mean flame shape if we set N to 7. You see overall we underestimate flame length and flame width a bit, but this is consistent across meshes. So our fully flame resolved simulation that has approximately 7 cells within the laminar flame thickness predicts virtually the same flame length and flame width as the flame on the medium mesh and on the coarse mesh, where we do apply the thickened flame models with F equals 2 and F equals 4 respectively. This is actually very nice because this confirms that the thickened flame model is consistent regarding the mesh resolution. Now, if I change N given the mesh, so I increase the thickening factor given the mesh, so given turbulence resolution and numerical truncation errors, etc., I see actually an elongation of the flame. So I decrease the local consumption speed if I increase the thickening factor given the mesh. Now, here you see I go to N equals 10 and N equals 15. You wouldn't do N equals 15 on purpose, but this is an illustration of what happens if you over thicken a flame given the mesh. And this may happen if you use an inadequate value for the laminar flame thickness in your model formulation, or if you use a variable grid spacing but a grid independent thickening factor F. To verify that this is not a coincidence, I also ran a case with N equals 10 on the coarse mesh, and you see virtually identical results on coarse and medium meshes regarding flame shape again. Now, first of all, this also means we can tune the factor N, or the resolution of the flame in the thickened flame model, in order to match experimental results if we know them. Now, mean flames are one thing. Let's now look at the flame dynamics. Here you see the flame transfer function grouped into 2 groups, because N equals 7 and N equals 10, as I've shown before, predict different flame lengths. We group them together. And you can see for N equals 7, the fully flame resolved simulation in orange here, and the simulation employing a thickening factor of 2 on the medium mesh predict very, very similar flame dynamics, so the gain falls into each other's confidence intervals, while the peaks and the troughs seem to be predicted slightly stronger on the fully flame resolved simulation. Once we go to the coarse mesh, there seems to be an underprediction in the gain after approximately 300 Hz. However, this is still really close to the confidence interval of the other two simulations, so I wouldn't interpret too much into that. Regarding the phase, you can see virtually identical phase predictions up until 300, maybe 350 Hz, and after then the coarse mesh predicts significantly different gain, especially once we pass 450 Hz approximately. For n equals 10, we again see virtually no difference qualitatively or quantitatively between the medium and the coarse mesh, as both the gain and the phase fall into within each other's confidence interval across all frequencies. However, a flame does not only live in terms of its flame transfer function, but also it has a whole spectrum of response. So here I plot the power spectral density of the normalized heat release rate when we change the thickening factor by changing n on the medium mesh. And you see here essentially what you would expect between the n equals 7 and n equals 10. In the higher frequency range, n equals 7 predicts more dynamics, while n equals 10 predicts less dynamics. This is sort of the no-brainer solution, but as soon as we increase n to 15, things change dramatically. Essentially, all the high frequency dynamics after around 200 Hz is dumped into the low frequencies with a peak of around 20 to 30 Hz. And this means the flame suddenly becomes extremely nonlinear and we can't identify an FTF anymore, which is also why I haven't shown an FTF for this flame. This also means that it's a really, really bad idea to use a fixed thickening factor on a mesh that is non-uniform. Okay, if we now change the thickening factor given n, so by changing the mesh, something more interesting happens in my opinion. Again, for the fine and the medium mesh, we see essentially the same heat release spectrum up until say 1500 Hz, after which the fine mesh predicts significantly more dynamics than the medium mesh. However, this is far beyond the frequencies that we care about usually. But if we thicken further to f equals 4 on the coarse mesh, you see after say around 400, 500 Hz, here the red line, the coarse mesh predicts significantly less flame dynamics than the other two meshes. So this damping that I mentioned before can manifest in turbulent flames for frequencies of a few hundred Hz already. So to summarize, in this presentation I've shown that cracking ammonia increases the FTF gain. So once ammonia is cracked, we do have to worry about thermoacoustics again. I've demonstrated that if we use a global chemical scheme with pure ammonia and 10% cracked ammonia, this global chemical scheme struggles in representing the accurate flame by overestimating the local consumption speed. I have shown that in a realistic turbulent case, the damping introduced by the thickened flame model can manifest at frequencies of approximately 500 Hz already in our case. And I've also shown that the dominant parameter governing flame predictions in the thickened flame model is actually the target grid resolution of the flame N and not the thickening factor F. With that, I want to thank you for your attention and thanks for tuning into this video.